Okay. Now the third reaction will be a new reaction, and I'll teach you everything in details. So the third reaction to prepare aldehyde that we will study now is called as Rosenmund reduction. What happens in this reaction is we take a acyl chloride, we take hydrogen, palladium as a catalyst, and we poison the palladium catalyst with barium sulfate. We'll see why. But if we do this, we get this and this. That means this H, one hydrogen from H hydrogen gas and Cl will come out as HCl, and one hydrogen comes here, and this gives us aldehyde. Effectively what's happening here is chlorine is getting removed and hydrogen is getting added. So this acyl chloride is going to convert into aldehyde. This becomes method of preparation of aldehyde, and this is an important method of preparation of aldehyde. Now let's see what happened here. The first thing is, when I taught you hydrogenation reaction, suppose if I had alkene here and I used hydrogen and palladium as a catalyst. Now this we understand why palladium is taken here. If you have forgotten, I'll tell you again. But if we do this, we get corresponding alkane. That means a hydrogen here and a hydrogen here is added on this. How does that happen? This hydrogen gas, when comes close to this ketone, and when there's a high pressure into the chamber where this alkene and this hydrogen is kept, under that high pressure, the hydrogen bond, being a weak bond, breaks like this. Each hydrogen will carry their one electron, and this pi bond breaks when these hydrogen approaches the alkene having one electron each, and the carbon and hydrogen now pair up and form a bond. So each carbon has one more hydrogen, and the pi bond is broken like this. One hydrogen increased on each carbon. So that's the method, that's the mechanism for hydrogenation reaction. Now the reason why we add palladium is because if we take a chamber like this, so alkenes or alkynes, whatever we are taking being heavy, will settle down, and hydrogen being a gas will be roaming around in the upper part of the chamber. So they two never meets up. When they two never meet, this collision will not happen and the reaction will not occur. The rate of reaction will be very slow. So to speed up the reaction, what we do, we add a palladium inside. Now this palladium will going to absorb this alkene, because palladium being a d block metal have attraction. D block metal have low shielding effect, so the nucleus attracts electron. Now when the nucleus attracts electron, in alkene and alkyne you have pi electrons, so those are attracted by the central metal atom. That's the reason palladium attracts alkene and alkyne. D block metal are also porous, and because of that porosity they also absorb gases. So hydrogen being a gas is also absorbed into palladium, and because of electron rich nature, this alkene is also absorbed on this palladium. So this becomes a common platform where hydrogen and alkene both meets each other, and when they meet they collide, when they collide they react, when they react we get alkane. That's how it goes. Now reason why we add palladium here is the same reason why we add palladium here. That's clear. The reason why we add hydrogen here was to get added on this pi bond. Now that's not the reason why we're adding hydrogen here, because there's no pi bond, and you don't dare to think that you're going to break this pi bond. This pi bond is a goddamn strong pi bond, because not less than 1,000,000 times I have told you before that C double bond O is the strongest double bond of organic chemistry. It is one of the most powerful factor which drives the reaction in a particular which drives the reaction towards a particular product, which dictates the mechanism of a reaction. So this C double bond O doesn't break under normal circumstances. So there is a pi bond, but this pi bond is not going to break by these hydrogens. right? Unless there's an extreme condition. There's no pi bond here, but the reason why pi bond adds hydrogen very easily, because they are weak. They can be broken under high pressure. Similar situation is here. We don't have a pi bond, but we do have a weak bond. The weakness of this bond is because oxygen has 2 lone pair, chlorine has 2 lone pair, and there's a lone pair excess in a small region. There's going to be a repulsion between oxygen and chlorine because of crowdedness of this lone pair. That's reason number 1. Reason number 2 is this chlorine doesn't fit well with this carbon, because this carbon is of second period, this chlorine is of third period, and there's a difference in size of orbital of carbon and chlorine. And we had this discussion before, that when there's a difference in size of the orbital, then the overlapping extent is decreased. The overlapping is not better. So if with bromine the bond will be even more weak, with iodine the bond will be very, very weak. So this is a weak bond because of less extent of overlapping between the orbital of carbon and chlorine. That's reason number 1. Reason number 2, there's a repulsion between lone pair of oxygen and chlorine. That makes this chlorine to go further away, making the extent even more less. Extent of overlapping even more less. Those 2 factors cumulatively makes this carbon chlorine bond weak bond. It's a weak bond, it can be broken easily. Fine. So intuitively you can think what happened here. This bond is broken, this Cl goes as Cl dot, one hydrogen comes to pair up with Cl dot, goes in the form of HCl, one H dot comes to pair up with the C dot, comes as CH. That's what has happened. Clear? So what has happened here is this bond is a weak bond. So under high pressure, hydrogens bond are going to break like this, and this bond is also going to break like this, and they're going to pair up like this. So this HCl goes away and this hydrogen comes in. This becomes a aldehyde. Clear? Clear. Now the reason why we added hydrogen and the reason why we added palladium is clear. The reason why we add barium sulfate is not clear yet. So it will be clear in a minute. Barium sulfate, I told you before a minute back that palladium is porous. Because of that porosity it absorbs hydrogen. And palladium nucleus, the positive charge of the nucleus in palladium attracts alkenes and alkynes because they are electron rich. Will attract acyl chloride because it is also electron rich, because it has a double bond, it has 5 lone pairs. So too much of electronic density. So that's going to be absorbed very easily. So this is going to be absorbed. The extent of absorption of acyl chloride will be very high. So they are going to be absorbed on the surface very quickly, get reacted very quickly. Now once they are formed, once they react, they form aldehyde. Now in aldehyde, chlorine is gone. So there is only 2 lone pair on oxygen and 1 pi bond. So the extent of electronic density on these 2 will differ very much because of these 3 lone pair not appearing in aldehyde. They are in acyl chloride. So this is less electronic rich than this. The extent of attraction would be less for aldehyde and will be greater for acyl chloride. Now if we poison the palladium catalyst, the surface of palladium, in such a way that this palladium absorbs acyl chloride but it does not absorb aldehyde, because the attraction for acyl chloride is higher. Now when we add barium sulfate into the surface, when we fill up the pores of palladium with barium sulfate, then the absorption capacity of this palladium will decrease. Now if we decrease it to such an extent that it still continues to attract acyl chloride because it has higher electronic density, but it doesn't have much of attraction for aldehyde because it has less electronic density. Now if we calibrate that poisonous of this palladium such that it attracts this, it doesn't attract this, then what happens is it will get attracted, will react on the surface. When it reacts, it forms aldehyde, and aldehyde is no more attracted. So it will leave the surface. When it will leave the surface, the chance of this C double bond O getting reduced further will decrease. So we'll have a pure aldehyde and there is no risk of this C double bond O getting reduced and we getting alcohol as the final product. Because if you reduce under very high pressure, if you reduce this C double bond O, then you are going to get this alcohol. There's hydrogen on this carbon and hydrogen on this oxygen. So RCH2 and OH. You're going to get this. So this risk is reduced because this aldehyde will no more be on the surface of palladium and there cannot be any reaction. Right? So this is Rosenmund reduction for you.